far as the vector stuff, that's all sort of making sense. Um, okay, so yes. Oh, okay. Number 2. Do you have the question with you? Okay, so working ahead is great, but you don't need to do the. I mean, I'll probably assign this stuff after today, but oh, did I? Oh, okay. Sorry. All right, number 2. So math. Number 2. So we have t squared x dot x is equal to 10. Oh, this is a system of equations, which is the first thing I'm going to talk about today. The let me say just a couple things about systems, and then I'll do this problem. So here's the problem. X at 1 is equal to 0, and y at 1 is equal to 15. So that brings up systems of ordinary differential equations. So systems of ordinary differential equations are you still have one independent variable. But you're solving for multiple dependent variables. So if the independent variable is, for example, let's say t, that's what it's always going to be for us in this class. And then the dependent variables in this class are most often going to be functions like x of t and y of t, maybe z of t, So that's how it'll appear in this class. So the key, okay, so can we solve these? Yes, if the equations are uncoupled. That means each dependent variable is confined to its own equation. Okay, so here's a coupled ordinary differential equation would be like or a coupled system of ordinary differential equations would be like x dot is equal to yt and y dot is equal to x squared t or something like that. Okay. You have y's in the x equation and x's in the y equation, so there's nothing we can do. Well, it's actually not super tricky to figure out how to do that. You'll do that in differential equations, and it won't be that hard. But in this class, we're not going to deal with it. Uncoupled would be like x dot is equal to, xt, y dot is equal to y squared t. It looks like the same kind of equations, but there are no y's in the x equation and no x's in the y equation. If the system is uncoupled, all you do is solve as two independent ordinary differential equations. So you can just think of them as like separate problems. Okay. Okay, so back to the example. Back to number 2. Here, this will be easier. Just do this with your magic pen. Oh, I don't even know how to do it. Damn it. Where's that at? Oh, here we go. Oh, yeah. Yes, it actually would have been faster for me to just write it. Okay, so look at this system of differential equations, 2 differential equations, and are there any y's in the x's or x's in the y's? No, this is uncoupled. So now you just have to make sure that that you can solve it by separation of variables. So I'm going to do x first. Do the equations just one by one. So the x equation says t squared x dot x is equal to 10. And we know that when t is equal to 1, x is equal to 0. That's the boundary condition that matters for the x equation. And so I'm going to write this as t squared dx dt x is equal to 10. And then I'm going to move all the t stuff to the right side, and we have x dx is equal to 10 t to the minus 2 dt, and integrate both of those. And you get x squared over 2. And I'm going to just combine the constants, so I'll put all the constants over on the right side. And negative 10 t to the negative 1 plus c. And now the boundary condition says when t is equal to 1, x is equal to 0. So plug those into this equation and you get 0 squared over 2 is equal to negative 10 times 1 to the negative 1 plus c. And so you get c is equal to 10. Yes?
Why didn't you move your 2 over first?
The 2 here?
Yeah, so there's x squared over 2. Why didn't you?
Well, I just, since we're plugging in 0 for x, that 2 just goes away. But I mean, yeah, I could have done that. I could have written it as x squared equals negative 20 times t to the negative 1 plus 2c, but we'd get the same value for c.
Oh, I thought if you multiply any number times c, it just is c. So
If you multiply it, oh, okay, it's a new c. It would be a new c. So it will work the same way as long as your constant means the same thing. It still would be an arbitrary constant, but it would show up in a different place. I could do that after I do this, and we can see how that would work. Yeah.
I just kept it when I put the 2 over. I just put the 20 instead of 10.
Okay, gotcha.
And the
Well,
answer's obviously not 20.
right. Well, that can be okay, but then if you go back to this equation to solve for x as a function of time, your new c is different than this. Your new c is 2 times this, you know? So you just have to be careful of, like, yeah, what you did is fine, but then what you're calling c isn't this anymore. Yeah. Okay, so c is equal to 10. Now we can plug it back in here, and we have x squared over 2 is equal to negative 10 times t to the minus 1 plus 10. X squared is equal to negative 20 t to the minus 1 plus 20. And so x is equal to plus or minus square root of negative 20 t to the minus 1 plus 20. And then that would be fine. But if you want to think about, would this function in the inside the square root ever be negative? You could worry about that. And it depends on your domain of t values. Okay, so that's the x value. We figured out x is a function of time. T could never be negative, but if you get close enough to 0, the thing in the square root gets negative. Well, in dynamics, if you ever get an x or a y position that's imaginary, you got problems. Okay, so let's do the y one. So now dy dt is equal to cosine of t. Where at time equals 1, y is equal to 15. So dy is equal to cosine of t dt. Integrate, and you get y is equal to sine of t plus c. And now the boundary condition says 15 is equal to sine of 1 plus c. So c is equal to 15 minus sine of 1. And actually, this brings up something that you need to know in this class and is useful in a lot of classes. Well, so now we know that y as a function of time is equal to sine of t plus 15 minus sine of 1. I would normally just give that as a decimal, you know, but that's the exact answer. Anytime you're doing derivatives with trig functions, you need, well, you know that you're doing it in radians. You need to be doing it in radians. If it's not in radians, you need to convert from degrees to radians first. Okay, that's because of the chain rule. So when you, when you take a derivative of a trig function, you take the derivative with respect to the stuff inside times the derivative of the stuff inside. And taking that chain rule step of taking the derivative of the stuff inside the function only works if you're in radians. Okay. So, yeah, just anytime you're dealing with trig functions and doing calculus with it, you don't have any option but to be in radians. Okay. So yes, you should, right, exactly. So you're just, so if someone asked you, like, how do you know, is this problem, are you, is that saying at 1 degree, the sine is equal, and how do you know? Well, no, it's in radians. And how do you know? Because I'm assuming the person who wrote that question isn't stupid. It's me. Okay. Any questions about any of the separation of variables stuff? Okay, so now we're done with most of the mathematical preliminaries. Actually, like, if somebody asks you a question, like, you guys are all transferring somewhere, and you're going to have to transfer into places where a lot of the students already have known each other for 2 years. So you got to sort of, so you can get into study groups and stuff, you got to sort of build a reputation. And saying stuff like that to people is a good way to do it, When they ask you questions, just call them out just brutally in front of everyone if you can. This class also offers life advice. Okay, so ODEs using separation of variables. This is all the topics for.
So,
yeah.
You use terms coupled and uncoupled as you did earlier.
Yeah.
That's not necessarily implying separation.
Right, okay. That's right. So you could have, uncoupled just means that the dependent variables stay in their own equations. Okay. But then you also could have, equations that are uncoupled, but you can't solve one or both of them by separation of variables. And then you have to use some other technique to do it. But if they're uncoupled, that just means that you can treat them as separate differential equations. You don't have to worry. You don't have to treat it as a system. Okay. Do the x's first, then do the y's, and they don't have anything to do with each other. Yeah. Okay, so the next thing we're going to do is talk about derivatives of vectors. in non-rotating coordinate systems. And then we're going to talk about product rule, and chain rule, both for vectors. Okay, we're done with this, and the rest is going to be pretty quick. So now derivatives of vectors. But you do have to remember that this only works in non-rotating coordinate systems. So if your vector is, so I'm going to use notation like this. You know, these are the components of your vector. Then to take the time derivative of that vector, all you do is take the time derivatives of the components individually. Okay. So that's pretty straightforward. It's what you would guess and hope it was you had to do to take the derivative of a vector. So here's just a quick teaser. Why doesn't it work for rotating coordinate systems? I think the easiest way to think of it is like this. If you think of, so let me use this other notation that I'm sure you've seen in physics before, that the meaning of that vector u is the x component times a unit vector in the direction of x plus the y component times the unit vector in the direction of y plus the z component times a unit vector in the direction of z. Okay, everyone's seen that notation before, right? So when you take a time derivative, these are products, so you have to use the product rule. And so what you get is ux dot times I, right? But now the product rule says also you have to add that to ux times I time derivative, okay? And then that's going on for all of these. Yep, that's exactly right. Yep. Okay, and so let me group these in a way that, so this says ux dot times I plus uy dot times j plus uz dot times k. And then we have another part grouping the rest of the stuff together. That's ux times I dot plus uy times j dot plus uz times k dot. Okay. And now I'm going to reformat this again. the first set of parentheses, we can, our usual notation says that we can write this as ux dot uy dot uz dot. But this second piece, we don't really have any way to deal with that. We don't have any special way to write that. If the coordinate system is not rotating, okay, then I, j, and k, those unit vectors aren't changing. Those are orientations of the coordinate system. So if the coordinate system isn't rotating, those time derivatives are 0. Okay, the time derivatives of I, j, and k are 0, and everything's good, and you're just left with that vector. Okay, but if the coordinate system is rotating, I dot, j dot, and k dot are non-zero, and you have to deal with that. And it, we'll talk about that later in the semester, but that's going to cause a lot of headaches, as you might imagine. Yes. Yes. No. Sorry. No, they would not. We'll go through that whole derivation later. It's yeah. Let's just. It's not. It's a little complicated. It'll make sense later. But yes. Yes, that is right, and that's a good distinction too. So we're not talking about thinking about it in two different coordinate systems. We're talking about one that's moving. Yep, where those axes over time are changing orientation. Okay, so the key thing is this is 0 for a non-rotating coordinate system, but non-zero if it's a rotating coordinate system. And that's why we're going to have to use this new approach for rotating coordinate systems. And you might think, so just don't use a rotating coordinate system. And in some cases, that is the answer. I mean, if you have the choice, that's definitely the answer. But in a lot of important dynamics problems, you don't get to choose where you put your coordinate system. So your coordinate system is where you're taking measurements from. And I think the easiest way to think of what a coordinate system is physically is like a video camera. This video camera is taking measurements. Okay. In some cases, it literally is a video camera or an infrared video system of video cameras. And so where your video cameras are mounted, that's where your coordinate system is. And if you can mount your video cameras to something that's not rotating, that's great. But sometimes you can't help it. And in fact, if you're doing very, very precise calculations on Earth, then you really, no matter where you put your cameras, they're rotating because the Earth is rotating. But that, for most applications, the Earth is non-rotating because it's rotating so slowly. It's going through 2 pi radians every 24 hours. That's a really slow rotation. But like if you're doing aerospace applications, then you're taking all your measurements from something that's spinning and flipping around in space. Those rotations are almost always very significant. And so the measurements that you get, you have to know how to correct for the fact that those measurements are being taken in a rotating coordinate system. So you don't have a choice. And so we'll get into how to do that later on. Any philosophical questions about that before I go on? So for now, all we care about is non-rotating coordinate systems, and the answer is easy. But for how to take a time derivative of a vector. the answer is easy. But later on, that question is going to be the thing that brings up this whole other area of looking at stuff. Okay, so now that's derivatives of vectors in non-rotating coordinate systems. So now the product rule for vectors. So there's a few ways that you can have products with vectors. You can multiply a vector by a scalar. You can do the dot product of two vectors, or you can do the cross product of two vectors. So if you're multiplying a vector by a scalar, this is actually the one that I just used in the little derivation right above. Okay, so what if you want to take the time derivative of something like x times the vector u? And by the way, another notation for this that you'll see sometimes is xu, and then a line over both of them saying, just making it clear that, and then a dot, just making it clear that that dot, that time derivative, is of both of these two things. You're not taking a time derivative of just x or just u. Yes. Yes, a scalar function of t. If it's a constant, then you know, derivatives are a linear operator, so you can just pull it out. Yeah. Okay, so the product rule here is, and the product rule, for the most part, it works the way you would expect that it would work. So it's x dot times the vector u plus x times the vector u dot. And actually, Liz, if you think about it this way, it could be a constant, and then that just makes the first term go away. Okay, so what if it's the dot product of two vectors? So then we have u dotted with v, and we're taking a time derivative of that dot product. This can be written u dot v bar and then dot over the bar. And this is equal to u dot dotted with v plus u dotted with v dot. And now the cross product. So d dt of the cross product u cross v. And you can write that with that other notation too. And this one is equal to u dot cross v plus u cross v dot. Okay, but the cross product you need to be a little bit careful of, because if you have, so with scalars, it's possible that, so like the product rule for x times y. Okay, so take the time derivative of x, y. You can think of that as x dot y plus x y dot, or you could, up until now, it hasn't mattered in the least if you thought about it as x dot y plus y dot x. Okay, and for all of these, that works. You can think of this one as x dot times the vector u plus u dot times the scalar x. That means the same thing. And the dot product, you can write this as u dot dotted with v plus v dot dotted with u, and that works fine. But it's not the same thing with the cross product, because the cross product is the only one of these where the order of operations matters. So here, it's not equal to u dot cross v plus v dot cross u. Those sweat globules indicate extreme stress. Okay, so I mean, I would recommend, because of this, and this kind of thing is going to come up more often with matrices and stuff in later classes. So if you have happened to get in the habit of thinking of the cross product as x dot y plus y dot x, just switch your thinking to keeping those same two variables in the same order, and things will work out with all the vector stuff then. And later when you get to matrices, it'll work out with matrices too. Okay.
Question.
Yes.
What is the distinction between
Dot product is scalar product. It's just two different things people call them. So people call the dot product scalar product sometimes just because the output of dot product is a scalar. And they call the cross product vector product sometimes because the output of a cross product is a vector. Yeah, just some people, sometimes you'll hear people call it that instead. Yeah. Same thing with, you'll hear people call dot product inner product and cross product outer product sometimes. Anyone have a guess why that would be? Well, if you think about what dot product measures, think about it in terms of the trig function. The magnitude of the dot product is the magnitudes of the vectors times the cosine of the angle between them. So the closer they're in the same direction, the more one is sort of like in the space of the other one, the bigger the dot product is. Okay. The more they're out of the same direction, the closer they are to perpendicular, the smaller it is. So, you know, so that's the in one. Like, how much are they inside each other? The projections. How much is the projection in? Cross product, if you think of the magnitude of that as in terms of trig functions, it's a sine. Okay. It's bigger if they're perpendicular and smaller if it goes to 0 if they're parallel. And so cross product is a measure of how much they're out of, you know, the projection is out of the other one. Anyways.
Does that go back to what you're saying with, what is it, value being positive if it's closer in angles and negative if it's wider?
Yeah, well, I'd say it really has, yes, it does. It has more to do with, so that it's bigger if the angle is close to 0, okay, and it's 0 if it's 90. Okay, so think of 90 as being all the way out of the direction of the other one, you know? Yep. Okay, so now chain rule. Chain of rule. Okay, so the chain rule says if you're taking a time derivative of a function f, and now this is a vector function, and f is a function of some g of t, we're only going to worry in this class about the vector function having an argument that's a scalar, but it's a function. We're not going to worry about that being a vector, although, you know, that does come up, but not in this class. So the way you calculate that is it's df dt, df dg times dg dt. So let me do an example of this one. So if you have so let's say that this vector f is equal to 2t, sorry. So let's say that this is like 2g and then g squared. So this is a function of g, and g is a function of t that's equal to t negative 5t. Then what if you want to calculate the time derivative of f? Well, no, this is a different example because so that g is a scalar. Let's just make that 5t. Okay, now it works. So if you want to take the time derivative of f, well, the first thing you could do is just substitute this in the first place and then take the time derivative. But there are times when it's nice to know, without knowing this explicitly to start with, how you would do this. So what you would do is take, this is a vector, derivative of f with respect to g times dg dt. And so that is 2g. And then we're multiplying that by dg dt, which is 5. And so what you get is 10g. And then you could substitute in the t. You could. So 10 and then 50t. Okay, but let me show you how this is going to come up in this class. So we're going to use this to calculate acceleration vectors from velocity vectors that are given as a function of, let me write in words, velocity vectors as a function of position. So normally, I mean, if you have velocity as a function of time, the way you get acceleration is you just take the time derivative and you're done, right? But what if your velocity is given as a function of position? Well, acceleration is not the derivative of the velocity with respect to a position variable. So what can you do? So for example, let's say that the velocity we know is equal to 2x x squared. Okay, so what that says is this object is moving as it moves, well, it's moving along some path, but the speed that it's going along that path is determined by where its horizontal position is. Okay, and that's a pretty common case. It could come up from doing using conservation of energy or whatever to calculate this. So what do you do to calculate the acceleration? Say we want to calculate the acceleration as a function of x. Okay. Well, we know that the acceleration is the time derivative of the velocity. We can't do that explicitly because we don't know the explicit dependence on time, but we can think of this as dv dx times dx dt and now dv dx is 2x. That part was easy. And what's dx dt? The x component of velocity. Yep. Right? Because velocity is the time derivative of the position. And so now we multiply this by 2x, and that says 4x squared is the acceleration of the particle for any given x position. And we did it by taking the time derivative without knowing any explicit time dependence. Okay, that's going to be a useful thing. Any questions about that? Okay. Okay, yeah, exactly. That's perfect then. All right, see you Monday. But you know, we'll talk about it more. That's what's coming up actually in the next couple of classes. We'll do that more of that stuff.